Hello, friends. Now, we've already done elimination reactions, right? Um, I would here talk about one very special type of elimination reaction which we have not discussed in the regular lectures. Before I take up with this reaction, which is then called E1cB, I would first of all want to talk about, in general, the beta elimination reactions. So, just a kind of recap, your beta elimination reactions that we've done so far, right? These are the ones in which we did E1, E and E2 reactions, right? Let me first of all give you a substrate here and let us understand what we did before. So, just a moment, let us put this as leaving group. There's this hydrogen, and these two could be any other groups. All right. Now, if we take let us, just a moment. Yeah. So let us take a base here. Now, if base pulls this hydrogen, this bond moves here and leaving group leaves. If everything happens in single step, right, then we get the alkene. Now this alkene, in which the leaving group has departed, and so we put it like this, that this plus BH and plus your leaving group. Now this kind of reaction, this kind of beta elimination reaction, which happens only in a single step, this is referred to as E2. On the other hand, the same substrate, if we take up, and if this reaction here, if this elimination reaction happens in a different way, in which first the leaving group departs, and this would give us, first of all, a carbocation, right? So you might get a carbocation here. You might get a carbocation, and this carbocation further, this is, let's say, step number 1, and in step number 2, you find that the base comes in and it eliminates the proton. The base comes in. Let me put a base here. And we get the product. This reaction happens in 2 steps, and we call this as, this is step number 2, we call this as E1 type of elimination. So E1 elimination happens in 2 steps, E2 happens in a single step. Now, we go to the third category now. The third category is a reaction which occurs in a slightly different manner. Let us take up this. And now, in the first step, the base pulls out hydrogen, and this is a kind of reversible step, and it would give us a carbanion. you can see that there is this carbon ion generated. This has a negative charge. Carbon ion which is generated here is actually a conjugate base of our substrate. So we also call this as, the conjugate base of our substrate. Substrate without hydrogen, conjugate base of substrate. Now in step number 2, you find that slow process and slowly the leaving group leaves and an alkene gets formed. So this is step number 2, which is a very slow step, and you get the product. Right? Now such a reaction which happens in 2 steps, right? However, you find that here the intermediate is a carbon ion or a conjugate base is referred to as E1cB type of reaction, which is what we will be talking about here, right? So now I hope you've understood what E1cB is all about. First, a proton is taken off, you get a carbon ion, and this carbon ion now would slowly have the leaving group pushed out and a double bond generated. This is also an elimination which involves an intermediate which is a conjugate base of the substrate, so it is called E1cB. One stands for unimolecular, right? So now if we focus on our E1cB, let us understand what this means. E1 here stands for a unimolecular elimination. And CB, it stands for the intermediate, which is a conjugate base. So conjugate base, which is the intermediate in the whole process. So first of all, you know now what E1cB is all about. Now I would take up a substrate and would try to explain when will E1cB take place. So before that, I hope I have taken up all the 3 processes, E1, E2 and E1cB. Our E1cB, if you focus on, is here, and E1cB will have a proton abstracted first, and then there is loss of leaving group in order to generate the product, which is an alkene, right? So now in the second part, we try to understand what requirement we have for our E1cB to take place. Yeah, the first step would be like, the first requirement would be like this hydrogen, because hydrogen is lost in the first step. You have to remember that this hydrogen should be lost easily. That is one thing. So when will this hydrogen be lost easily? It will be lost easily because here this is the alpha carbon, this is the beta carbon. So if you want this hydrogen to be lost easily as H+, it has to be really acidic. So this has to be, should be acidic. Right? So how can you make this acidic? Only when you have this electron withdrawing groups attached to beta carbon. So that's one of the requirements. In order to make this hydrogen acidic, you have to have electron withdrawing groups attached to beta carbon. Now what are the normal electron withdrawing groups you come across? one of them being NO2 and CN. These are some of the electron withdrawing groups. You can even have your beta carbon connected to a C double bond O. If your beta carbon is connected to a C double bond O, it would also make the hydrogens on beta carbons extremely acidic. Or you can have anything like, SO2PH, which is also a group like SO2PH, which should be connected to your beta carbon. So these are all some groups which would make the beta hydrogen acidic, right? That is one condition. What is the other condition? The other condition is leaving group. See, before the leaving group leaves, your hydrogen has to leave, right? So this should not leave easily. So this should be normally a poor leaving group. So leaving group should be poor. It should not leave easily. So let us make a list of some poor leaving groups, right? One of them being OPH, OCH3, OH, fluorine F is also a poor leaving group, right? These are all very poor leaving groups. So two things, if your hydrogen is acidic and if you have a poor leaving group, strong acidic hydrogen on beta carbon and very poor leaving group, right? In that case, E1cB can be observed. Generally, the reaction conditions, one of the reaction conditions that you should always have is you should always have a strong base. Strong base used. Now, what are these strong base? Strong base is, you have either OCH3 minus, OC2H5 minus. You can have NH2 minus. These are all strong bases. You can even have alkyl lithium. In fact, CH3Li, where CH3 has a negative charge on it, right? These are all extremely strong bases, right? And what else would you need? You would also need some high temperature because this is elimination. So these are the ideal conditions for E1cB to take place. So you make a note of this. You always have to have a copy to, have a notebook with you to write down all these things. These are very important things. Okay. Now, the next we go to the exact mechanism of how it works, and then we would take up the kinetics of this process as well as some examples. So now, let us take up an example of one of such elimination reactions. We take a substrate here where, the alpha carbon has 3 fluorines attached, and then the beta has a hydrogen on it and 2 chlorines, right? Now, what would be the first step? The first step would be a reversible process in which you find that this is pulled out and a carbon ion, the intermediate, gets formed. Look at this. Now, just remember one thing. Here, the stabilization of carbon ion is very important. So you can see that the carbon ion here is extremely stabilized because of two things. One, any carbon ion is stabilized when you have a strong electron withdrawing group. Now imagine CF3. CF3 is extremely electron withdrawing and it can stabilize this anion extremely well. Another thing, chlorines. Each chlorine will have an empty d orbital, right? And therefore this lone pair is partly, in resonance with that empty d orbital. So this lone pair then gets delocalized over the d orbitals of both these chlorines, which makes it even stable, like even more stable. So this is kind of like, extremely stable conjugate base. Stable conjugate base. So you need to understand that your base has to get stabilized. If it doesn't get stabilized, it may not easily get formed, right? Now it is a time for the leaving group to leave. Now any one of these fluorines is a leaving group, right? So now let us put up, this was the step number 1. And now there's this step number 2, which is a slow process. In this slow process, you find that your chlorine, this is one more chlorine, lone pair, negative charge, fluorine, and the remaining 2 fluorines. Right. Now this is going to be a slow process because fluorine is a very, very poor leaving group. So now you have your lone pair slowly trying to make a pi bond and fluorine going out. So what do we get now? We get, C, chlorine and chlorine, a double bond, C, fluorine, and one more fluorine. And, plus F minus. Here I could have even, in the first step, I could have written plus CH3OH. Yeah, I could have written that. So that's okay. So this is the mechanism. You can see that, the first, there's loss of proton, and then there is this loss of leaving group. I hope you've understood this mechanism properly, right? Okay. We now go to the kinetics of this whole process. Let us now understand the kinetics of E1cB. So what we do here is, let us assume that our alkyl halide, whatever we take, let us call this as Rx, right? And let our base be B with a lone pair and a negative charge, right? So this is any alkyl halide with all the requirements that we need: acidic hydrogen, poor leaving group, everything there, a strong base, and there is this first step, reversible step, and you get an intermediate, which is nothing but our conjugate base. Right. And in step number 2, our conjugate base, right, will have the leaving group gone, and it would slowly get converted into product, which is going to be an alkene, right? So I am just putting a general equation, so don't worry. I'm just trying to put a general equation of how it exactly works. So, yeah. So don't worry. This is our conjugate base and this is our product. Now, let us take the kinetics. You know that rate of the overall reaction depends on the slow process. So let the rate constants be given here. Let this be K3, let this be K1, and let this be K2. So rate of the overall reaction would be K3 into concentration of intermediate. But you know that rates cannot be given in terms of concentration of intermediates, because rates or rate law can only be expressed in terms of either concentration of reactants or products or even at times catalysts, but never you express your rate law in terms of concentration of intermediates. So we need to remove this. So we need to remove this concentration and replace it with either the concentrations of reactants or products or whatever. So for that, we take up the first equation every time, right? This is an equilibrium governed equation, and at equilibrium, so considering equation 1, right, at equilibrium, rate of forward process will be equal to rate of backward process. So what is rate of forward process? K1 into Rx, which is your alkyl halide, and B minus, which is the base taken, and it should be equal to K2 into concentration of intermediate. Therefore, concentration of intermediate here can be given as K1 by K2 into Rx into B minus, right? And we need to put this, here. So we get the final rate. Final, what we get is the rate law is K3 into K1 by K2, and this should be Rx and also B minus. Okay, so what kind of reaction will this be? It be a second order reaction overall. It's very important. However, because in the rate determining step, the slowest step, there is only one species involved, it will be a unimolecular reaction. So basically, unimolecular reaction as well as second order kinetics, it follows. Very, very important. So the rate of such reactions would depend on concentrations of both this as well as this, but it would still follow, it still would be called a unimolecular reaction, although it follows a second order kinetic, right? So that's it about kinetics. Now we take up some basic examples of this E1cB. Okay, one of the simplest examples of this could be a molecule in which there is fluorine taken as a leaving group and CH3. So you do have a leaving group, a strong leaving group, and now when you react this with, let's say, something like OCH3 or OH in alcohol, and you have to react it at a high temperature. Now the point is, there are two beta positions here, right? And if E2 is followed, we normally would go by, there would be Sedzev's elimination, which would be dominating here. However, here, proton is lost first. And because proton is lost first and a carbon ion is generated, where would the carbon ion be more stable? So we have two options. If this beta hydrogen is removed, right, let's see what happens. And if this beta hydrogen gets removed, let's see what happens. If the first one gets removed, we get CH2, a carbon ion, CH, fluorine, CH2 and CH3. And if the second one gets removed, then you get CH3, CHF, CH lone pair and CH3. Now look at this. This is a primary carbon ion and this is a secondary carbon ion. You know the stability of carbon ions. Primary is more stable than the secondary. So this is going to be your major product and this is going to be your minor product. So if we only talk in terms of major product, your major product would be like this. Now this lone pair goes here and this is going to be your major product, CH2, double bond CH, CH2 and CH3. And if you go by this second method, right, you find that this comes in and this goes off and you have your minor product like this. Just remember, this is major and this is minor. If you look at this product here, you know that because of E1cB, Hofmann predominates. So Hofmann's elimination predominates. This is Setzev, which is less. Setzev's elimination here will be less. Okay, so this was the first example where if they ask you major product, you have to answer it like this. You have to give the major product most of the times. Okay, let us take up one more example. Such a molecule is called an aldol, and now let us understand how this goes. Now you can see that this is your poor leaving group that you see here. This is your poor leaving group, and now this is your alpha position and this is your beta position, and beta carbon has an excellent electron withdrawing group attached to it, which has its own advantages. We would see what exactly happens here. Now the first step would be the loss of one of the beta hydrogens and formation of carbon ion. So let us understand how this happens. So the first step here would be CH3, C double bond O, CH, all lone pair, negative charge, CHOH, and CH3. The next step would be, there is resonance stabilization. So there is formation of, an alkoxide here, right? So let us put this together, right? And I have not put a reversible sign, but there has to be a reversible sign. And then you can have this strong O minus and double bond CH, and then CH, OH, and then CH3. In the next step, now you will find that this comes over here, this shifts here, and this moves out. And therefore you have your final product, CH3, C double bond O, CH, double bond CH, and then we will have CH3. Now you can see that the product is conjugated, which makes it extremely stable and which also allows such reactions to occur very, very easily, right? This is also an example of E1cB, right? So elimination of aldol follows the same thing, right? One of the other examples that I have here is an example in which we have, a strong withdrawing group and a poor leaving group. A strong withdrawing group would make our H extremely acidic, and we have a strong base taken, heat. So the first step would be this, right? And then there would be carbon ion generated. So I am going to put it like this. You have double bond O, and then carbon ion. Let me every time put this here, that there is this reversible step, and you always have carbon ion. Chlorine would stabilize this carbon ion. This is CH2 and F. In the second step, now it'll be like slowly double bond gets formed and leaving group departs, and this is going to be a slow process in which you find that there is SO2, and then there'll be Cl, double bond CH2, and this is how we get our product plus F minus, the leaving group. Okay, so taking these examples, I hope you might have understood everything. And here I have to end the lecture. If you have any doubts, you can always ask when I am there in my institute. So that's it. Thank you.